Okay, going to go over the answers here for the practice test. Well, these first couple of questions are talking about some elements, and like a lot of the questions on this test, they depend on you knowing where they are on the periodic table. So we're going to kind of make a mini periodic table here for ourselves. Okay, we've got beryllium, we've got boron, we have carbon, and we have silicon. So those are the elements that we need on this one. So who has the smallest atomic radius? Well, the smallest atomic radius is going to be the one most right and most up, and that's going to be carbon, and carbon happens to be answer C, so that's the first one. Second one has an electron configuration of 3s2, 3p2. Well, we can see that's going to have 4 valence electrons, so somebody from the carbon family. So it could be carbon, except it says neon, so if we could see the entire periodic table, we would know that if it was carbon, it would be helium 2s2, 2p2. So this must be silicon, and silicon is 3s2, 3p2, so that is going to be answer D. Okay, the largest ionization energy would be C, would be the same as the smallest size. And there's 2 valence electrons. Well, these guys have 4, this has 3, so it must be beryllium, and beryllium is answer B, so this guy is answer B. Now for our true-false questions. Okay, so here in cobalt atom, the electron furthest from the nucleus is the 3d, and cobalt, the valence electrons occupy the 3d. Well, we really have to go back and look at the periodic table and say, okay, here's cobalt. So cobalt's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 3d7. So the valence electrons are going to be out here in the 4s. So let's go back to here. The furthest from the 3ds, no, they have electrons in the 4s, so that means that the 4s are going to be farther out than the 3s. You know, 4th floor electrons are farther out than 3ds, so that's false. And the valence electrons occupy the 3d, that's also false. This is a false statement. Okay, number 6, there are 4 orbitals in the 4d subshell. No, d's, okay, now the 4 doesn't have anything to do with it. The d subshells always come in 5s, so this is false. 10 electrons can occupy the 4d subshell. That's true. D's always come in 5s, and since each one can hold 2 electrons, then that would be 10 electrons altogether. So it's false true. Fluorine has a higher ionization energy than oxygen. Well, we have to go back and say, well, where are those on the periodic table? And they're right next to each other. Okay, O and then F. Then after that would be neon. So fluorine has a higher ionization energy. That is true. Okay, farther to the right, greater Z effective, more protons in the same shell. That's going to be harder to remove an electron. Fluorine has more valence electrons than oxygen. That's also true. Okay, fluorine has 7, oxygen has 6. But this second statement does not explain the first statement, so it's just true, not true, CE. Number 8, here's a calculation. It says, what is the energy in joules of a photon of light with that frequency? Well, frequency is that little V-shaped thing. So to do this, we have to do a calculation, and we're going to say that energy is equal to Planck's constant times nu. So that's this number, 6.6 times 10 to 6.626 times 10 to the minus 34 joules times seconds. And the frequency is 8 times 15 10 to the minus 1. Okay, so we have to calculate those two. And when you do calculate them, you get answer C. Okay, 5 times 10 to the negative 18. So we substitute in these two values, and you get answer C. For number 9, which of the following forms of light has the greatest energy? Well, this is a couple of parts. So here's some frequencies. We know the higher the frequency, the greater the energy. So 10 to the 9th is going to be greater than 10 to the 8th, so we can eliminate cell phone bands. Of these two wavelengths, we know the smaller wavelength is the higher energy. So this is a very large wavelength, 10 to the minus 1. So it's going to be one of the two next ones. And now we actually have to go back and calculate and say, okay, I can do E equals H nu for that one. And for this one, we have to use a slightly different version, E equals HC over lambda. Or what we can do is to take the lambda, change it into nu, and then use E equals H nu. But either one, we have to do both calculations. And when you do, you're going to find out that C is a better answer, higher answer. Number 10, what is the maximum number of electrons that can fill the 4f orbitals? Now again, it doesn't matter that it's a 4. Okay, that doesn't make any difference at all, just f orbitals. So f orbitals, f's always come in sevens. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can always get 14 electrons in any of the f orbitals. Okay, which is the correct electron configuration for S2 minus? Okay, well, S2 minus, okay, it means we're going to have 2 more electrons in. And if we go back and look at where S is, okay, S is way over here. And so S2 minus is going to have the same electrons as argon. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, or neon, 3s2, 3p6. So what answer do we have here? We have neon, 3s2, 3p6. Okay, same as argon. Number 12, which of the following electron configurations is correct for a ground state neutral atom? So now we have to go through and see who is filling these up correctly. So first one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, it should have gone to 4s2, so that is not the answer. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That sounds good. I think that is the answer. Let's double check. C, 1s2, 2s2, 2p6, 3s2, 3p6, 4s4. Okay, you can't fit 4 electrons in the s orbital, so that's no good. And 1s2, 2s2, 2p6. We're missing the 2p6, so that's not a good either. So the only one that could be correct there is answer B. Okay, electrons are placed in the orbitals correctly. Okay, well, here's our orbital. We have s orbital, we've got p orbitals. What are we going to do? Put first one here. That's not in it. Here's here. Okay, that looks like answer C. Okay, after that, we would put 1 in each one, and then we would double them up. So we can look, A is not correct because we should have doubled up the first orbital before we filled them up, so that's no good. B, totally skipped the s orbital, that's no good. And D, we should have put 1 in each one before we start doubling up, so that's no good. So the answer is C. Okay, that was the only one that's correct. Which group of elements forms -1 ions? Okay, -1 ions, not the noble gases, they don't form ions. Alkali metals form 1+ ions. Alkaline earth metals form 2+. It's the halogens that are 1-. Okay, it's answer C. Okay, for 15, okay, when we have chlorine and Cl-, okay, why and how does the size change? Well, okay, if we become Cl-, you're going to get bigger because you have more electrons. Both of these have the same number of protons, 17, but to form an ion, form chloride ion, you gain an electron, so you have more repulsion. So we can knock off smaller and smaller, and it's bigger because we have more electron repulsion. That's the answer. B, more electron-proton attraction. If that was true, we would expect our atom to get smaller, so that's not the right answer. Answer A. Okay, 16. This could be what? S, P, D, or F. The 1, 2, 3, 4 makes no difference. Okay, so this is spherical. Spherical is an S subshell. P orbitals will look something like this, you know, in the y-axis and the z-axis. D orbitals are kind of like 4-leaf clovers, and F orbitals are kind of weird. We just say forget it. So spherical, perpendicular, diagonal, and forget it. For 17, where are the largest atoms on the periodic table? Well, we know that they get larger as you go across and they larger as you go down. That is wrong. Okay, let me repeat, let me go back. Okay, they're larger, they get smaller as you go across. So they're larger to the left and they're larger down. So the largest atoms are down here in the lower left, like francium. So lower left is the right answer. Okay, 18, here's a kind of a strange graph, and that is the ionization energy of the different elements. So now the ionization energy, we know as you go across any row of the periodic table that the ionization gets higher and higher and higher. So the noble gases have the highest, the alkalis have the lowest. So if you look at this graph where you go from, you know, first element all through, every time you get to a peak, then that's a noble gas. And every time you have a little valley, okay, those are the alkali metals. And so we're asking who are the alkali metals? Answer is W. If we were asking for the noble gases, it would be X. 19, which of the following elements has the same number of valence electrons as carbon? Okay, so that means we have to look at the periodic table, and we want somebody that's in the same row as carbon. And let's go back and look. Okay, carbon family. So it could be carbon, silicon, germanium, tin, or lead. Okay, and the only one here is lead. Lead's in the same family as carbon, has 4 valence electrons. And it makes sense because we know that lead forms a 4+ ion as well as a 2+ ion. Okay, these next two questions, here's a little piece of the periodic table: selenium, bromine, tellurium, and iodine. Which has the largest atomic radius? We know largest radius is to the left and down, so it's going to be tellurium. Which has the largest ionization energy? Well, that goes with the smallest atom, so it's going to be to the right and up. It's going to be bromine. The largest ionization. It's going to be hardest to pull it off of the smallest atom. 22. Consider iron. Okay, the electrons in iron that are farthest from the nucleus occupy which orbital? Well, this means that we know what iron looks like. Okay, so let's go back to our periodic table. Here's iron. Okay, so iron, where it is, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. So iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So we have to know that before we can answer our questions. So the electrons that are farthest from the nucleus, okay, there were electrons in the 4s orbitals. There were none in the 4p, so that's not a possibility. And 4s are farther than 3s, so that's the answer, 4s. The electrons that have the highest energy, well, okay, the last ones we put in, those would be the highest energy. Those were going into the 3d, so that's the highest energy orbital. 24, how many orbitals are half filled? Well, we're talking about these, all of these are totally filled, as we fill them up, fill them up, fill them up. So it's not that. It has to be the 3d and 3d6. So if we have d orbitals, 5d orbitals, we go 1, 2, 3, 4, 5, and 6. So that leaves us with 4 of these that are only half filled at 1 electron. And how many valence electrons does iron have? Okay, we did have electrons in the 4s. Those were our valence orbitals, the farthest ones out. And so there were going to be two valence electrons. Okay, 26. Now we're talking about a different element. Okay, we say what's happening. Which element could this be? Well, the clue is this is 700. This is 14. It went up by 700. But this one went up by thousands. Okay, that means these 2 electrons were relatively easy to pull. They were in the outer shell. They had 2 valence electrons. And so we say, who has 2 valence electrons? Neon has 8, sodium has 1, magnesium has 2, aluminum has 3. Okay, so the fact that we had a big jump after the second ionization energy means that there were 2 valence electrons. That makes it magnesium. Okay, for 27, okay, we're talking about tungsten. Okay, well, finding tungsten on the periodic table, tungsten is way down here. Okay, so that's going to be a big atom. Okay, one of the lines in the emission spectrum of tungsten, okay, is the X-ray frequency has a wavelength of this. Okay, so all that initial stuff is not very important. You say, here's the wavelength, what's the frequency? Well, we know that frequency times wavelength equals C. So we want the frequency, so frequency is equal to C divided by wavelength. So we're just going to substitute in our numbers. So 3 times 10 to the 8th meters per second divided by wavelength, which is, we just said 2.14 times 10 to the negative 11th meters. So meters drop out, and we're going to be left with seconds to the -1 or hertz. Those are both the same thing. And the answer to this is 1.4 times 10 to the negative 19th joules. Not joules. Seconds to the -1. I'm sorry, that's not negative, it's positive. Okay, so get that out there. So 1.4 times 10 to the 19th seconds to the -1 or hertz. Now what's the energy of this light? So we know energy is equal to H times nu. And so energy is equal to 8, so that's 6.626 times 10 to the 34th, 10 to the negative 34 joules times seconds. And this whole thing is times 1.4 times 10 to the 19th seconds to the minus 1. So we can see that our seconds drop out. Okay, we're going to left with joules, and we get all done. The answer is 9.3 times 10 to the negative 15th joules. So it's just a calculation. Okay, for tungsten, we want our long form and our short form. Okay, well, we're going to have to go back here, and I'm going to take a second and clear off all of this ink. Okay, we want to do tungsten. So for tungsten, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4s, 4d10, 5p6, 2, 3, 4, 5, then 6s2, 4f14, and then we have D's 3, 4, 5, 5d looks like 4. Okay, so let's go back and write that answer in. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, oh boy, 4d10, 5p6, 6s2, 4f14, 5d4. Okay, if you really want to read that, look at the answer key online. Okay, the short form for this, and thank heaven there's a short form. Okay, tungsten, we go back to radon up 1 is xenon. And xenon covers all of this all the way up through the 5p6. So it's xenon, 6s2, 4f14, 5d4. How many valence electrons? The valence electrons are going to be those 6s. Okay, so the 2 and the 6s, so there's 2 valence electrons for those. Now what if we had tungsten 6+, okay, the ion tungsten 6+, so we're going to lose 6 electrons. Who are we going to lose? We're going to lose the outermost electrons. So we have the, I'm going to try to draw it normal. So xenon 6s2, 4f14, 5d4. Okay, we're going to lose the outermost ones. We're going to lose those 6 s's. And then we still have to lose 4 more. We're going to lose the 4 and the 5d. Okay, so our final answer here is going to be xenon 4f14. And that's our answer. Okay, which is expected to have a larger radius, tungsten or tungsten 6+? Okay, so both of these have the same number of protons in the nucleus, and it happens to be 74 protons. It doesn't really make a difference right now, but they have the same number of protons. But if you become +6, that means you have lost your sum of electrons, so there's going to be less repulsion, and it's going to make it smaller. So the larger one is going to be tungsten neutral, okay, because with the same number of protons, okay, tungsten has more electrons, okay, and therefore more electron-electron repulsion. And that is going to make it a little bit larger atom. Okay, 28. Make a prediction for each of the following and then explain. Okay, which has a larger radius, rubidium or strontium? Well, we have to look on the periodic table and find those two. We're going to find out that rubidium and strontium are right next to each other. Okay, so who's going to have a larger atomic radius? Rubidium. And why? Because it has fewer protons with the same shell, or we can say it has a smaller Z effective. Okay, fewer protons with the same shell. So that means that the outer electrons are going to be pulled in a little bit less because of the fewer protons, and that's why it's going to be a larger atomic radius. Okay, B, which is a higher ionization energy, selenium or tellurium? So again, we need to look on the periodic table, and we'll find them over there, 34 and 52. Selenium and tellurium is right below it. So which has a higher ionization energy? Well, as you go down the periodic table, you get more and more shells. So selenium has fewer shells. Okay, and since it has fewer shells, that means that the electron is going to be more difficult to pull off because it's closer. Okay, the outer electron is closer to the nucleus, and that's going to make it more difficult to pull off the electron from selenium. Selenium has a higher ionization energy. Okay, and C, which has a smaller radius, chloride or potassium? So we're going to look at that and say, well, chloride is one element less than argon. So chloride has the same number of electrons as argon. Cl- has the same number of electrons. And potassium is the next element, and that has one electron more neutral than argon, but if it has plus, that has lost one. So chloride, argon, and potassium all have the same number of electrons. They all have 18 electrons. So which is smaller? Okay, the smaller radius is the one with more protons. Okay, so potassium has 19 protons, okay, where chlorine only has 17 protons. So the more protons you have, the smaller your radius is going to be. So the answer is potassium ion, okay, because it has more protons with the same electrons, same number of electrons. Okay, it's going to have greater electron-proton attraction, and that will make it smaller. Now again, on your table there, you have this little chart, and again, that's to help you, because you can remember to do 1s, 2s, 3s, 4s, 5s, 6s, 7s. Okay, your P start with 2, 2p, 3p, 4p, 5p, 6p, 7p. Your D start with 3s, 3d, 4d, 5d, 6d, and the F start with 4, 4f, 5f. So like when we just did tungsten a moment ago, okay, tungsten was way over here, and so we went, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d4. So we can use that chart to help us write out our electron configurations. And that is the entire practice test.